Good afternoon, everyone. It's my pleasure to be here. I'm Kate Maher. I'm also from the School with Good Questions, apparently. I'm a professor in Earth System Science and part of the Sustainability Data Science Working Group. So it's my pleasure to introduce our first speaker, and this is Professor Brad Efron. He is a professor in statistics in the School of Humanities and Sciences, as well as a professor of biomedical data science in the School of Medicine. And I'm very intrigued by the title of his talk, which is Not Quite Reproducible Research. So welcome.
Thank you for the introduction, and thanks to people for putting together this very nice day. It says not quite reproducible research. It goes back to a paper, very well-noted paper by John Ioannidis from our medical school, from our Biomedical BDS department. And the title of Why Most Discovered True Associations Are Inflated, a very provocative title, and he gives good reasons to believe that, in fact, reported effect sizes, when you check them later, seem to retreat towards zero. And I wanted to give this talk because I read a very fun paper in statistical science and then looked it up by Eric Van Zwet and a bunch of co-authors, including our own Steve Goodman, it's called The Statistical Properties of RCTs, Randomized Clinical Trials, and it gives an intriguing explanation as to why this might be the case. And so that's pretty much what I'm going to tell you. And Eric's analysis followed from the good idea of going to the Cochrane database of systematic reviews. And the Cochrane Institute is people who do incredible good. They collect, in this case, some 8,821 z-values from randomized clinical trials. That is, the model is that they're seeing zi, and it came from a normal distribution with true effect size mu i and variance 1. So you'd like to know mu I, but you get to see zi. And what Ioannidis said really is you better guess that mu I is less than zi, closer to 0. And so the question is, if, say, we observe, say, zi equals 3.5, what should we believe about mu I? And here's the blue histogram is the histogram of the 8,821 z-values. And it looks pretty normal, but in fact it isn't really. It's got long eccentric tails. I've cut them off at about plus or minus 9. And the tails are heavy and rather irregularly formed. The black curve is a fitted smooth curve to the histogram, and I'll tell you where it came from soon. So so there we have, there's the histogram. We wish it was a histogram of the mu i's, but of course it's a histogram of the z i's. And then the idea is, well, let's deconvolute it to get at the mu i's. What does that mean? Well, we'll take the Bayesian model where we have some hidden prior density g of mu that's actually given the mu's. And for any one mu I, it comes from g, but we don't get to see it. We get to see zi normal mu I 1. And that is, it's centered at mu I, but it's got noise on it, plus or minus noise. And if we knew Bayes' rule, if we knew g, we could just use Bayes' rule to get the density of the posterior density g of mu I given zi, and there couldn't be any more argument about what that means, right? That's the answer. But we don't know g. We can't see it. And the idea is to deconvolve the Cochrane database and try and get out what g is hiding there underneath the z's. And and that's where Neris and I come in. this is our wheelhouse now, so that we've written a paper on and have an R CRAN package called deconvolver, which does exactly what this is supposed to do. It deconvolves the Z's to give the mu's, and presumably does a good job of that. And the paper is fun to read, and it isn't hard to use the package. So what does it mean to, here specifically, this is the only specific thing in this talk. The model used here is that the log of g of mu is a polynomial in mu, and it's a 9th degree polynomial in mu. It goes up C0 plus C1 mu plus C2 mu squared, dot, 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 plus C9 mu 9 to the 9th power. Why to the 9th power? Because the 8th power didn't work. Neither did any of the lower ones. You'll notice if I stopped at 2, I would be saying that the prior was in a normal family. So you need all those extra ones in trying to model the long tails of the z values. And now, if I tell you in the second line there, it says C, that's a bold-faced C, that's 10 numbers, C0 through C9. If I tell you those 10 numbers, that specifies G sub C of mu, the prior, and that gives the marginal density F sub C of Z, which is the prior, which is G sub C convoluted with normal 0, 1. Just exactly what we think the model is. And now all we have to do is get the likelihood, that's in the 4th line there as a function of C, try all the C's and see which one maximizes the likelihood. And there's a little more to it because you have to do some regularization to avoid getting stuck, but that's pretty much what was done. And here it is. Here's the estimated Cochrane prior. And it's pretty normal looking itself, except it has long tails sticking out there. It's got a variance a little less than 1. That's the heavy red curve. And then the dashed light curve is the corresponding F. Of course, it's not, because each Z is a noisy version of mu, the dash curve is wider and lower than the red curve. And so it says there F of Z, and that's the curve, that's the black curve that was fit there. And do we think it's pretty good? Yeah, you can do a goodness of fit test, and it doesn't really pass, but it comes close, and with 8,800 things, that's usually good enough. Okay, so what? Well, now we have the prior, and now we can pretend that's the true G, and we can use Bayes' rule. And I will use Bayes' rule. And here's the red curve. The horizontal axis here is the observed Z value. At the far right, Z equals 4. At the far left, Z equals minus 4. The vertical axis is what we believe mu is. And the red curve is the median of the posterior distribution, 50% more or 50% less. And you can see what it looks like. The light straight line, light dash straight line, is the 45-degree line. If the red curve fell along that line, then Ioannidis would have been wrong, and there wouldn't be any regression to the mean. That would be the case. If you saw Zi equals 4, you should guess 4 for mu I. But that isn't the case. In fact, you can see that there is some regression to the mean. If you see Z equals 4, the red curve is about 3. If you see Z equals minus 4, the red curve is about minus 3. And the black and the two black curves are the 5th percentile and the 95th percentile of the posterior distribution. And you can see it's sort of like a translation family. Things seem to move up in parallel. So here's a rule of thumb. So you can interpret the Ioannidis hypothesis. If you see a zi, the median of mu I is about 1 unit moved toward 0. So if you see z equals 3.5, you ought to guess 2.5. If you see z equals minus 3.5, you ought to guess minus 2.5. And that's a pretty good rule, I think. And so now let me go back a second. It says there, hypothetical, suppose a startup pharmaceutical firm observes, they're just getting going, they've invested all their money, they have a new drug, they think it's great, they've run a phase 2 trial, and they maybe have 100 people total in it, and they get their z-value versus the previous standard of care, and it's 3.5. And they're pretty excited about that. And so what should they believe? And at that point, you have a choice. Well, of course you have a choice. And here's 2 choices. The red dash curve, the pharma company very rationally might believe that they don't care about the Cochrane database. They just have their own experience, which isn't very much. And they think that they're going to use a flat prior distribution across the whole all possibilities. And if that's the case, the posterior density is that red curve, which is normal. They've seen 3.5. The red curve is normal 3.5 with variance 1, which is just say it's the usual frequentist answer that would be given. And I think that's a perfectly rational thing for them. However, you might be a venture capital firm thinking about investing in them, and you might care pretty much about the Cochrane database as past experience, in which case you might use the formulas that we had before, the prior that we got for the Cochrane, and that's the black curve there, and it's a good deal less optimistic than the red curve. Its high point is about 2.68, I guess. My rule of thumb was a little strong there, but it's not symmetric. There's more downside than upside there. And I think both answers are perfectly reasonable in their context. It's not just pharmaceutical, not just venture capitalists who might feel this way. There's also the question of the, say you're the FDA. What do you think you're going to think about that? Or suppose you're just a reader of the New York Times, a regular. They always have, every Tuesday, they have tons of cases like this. And people reporting things. What do you believe about that 3.5? The Cochrane database might be a better guess. So that's what I have to say, except to thank the organizers once again for a very pleasant afternoon so far, and particularly thank Chiara for all the work she did here. So thank you.
And I probably should have mentioned this. I think everyone knows we will have a question and answer period for our 4 speakers at the end of the session. So if you can hold those questions in your head until the end, we'll have a chance for discussion. So it's my pleasure to introduce our next speaker, Heidi Williams. Heidi is the Charles R. Schwab Professor of Economics in the School of Humanities and Sciences and a professor by courtesy of law. And Heidi's title is What Inventions Are We Missing?
Thank you. I'll avoid getting in a fist fight about which field has the most important questions, but if you would like to talk to Hito and I about economics during the Q&A, we would love to answer questions. So I'm an economist by training, but my research is very interdisciplinary, basically focusing at the intersection of science and medicine and law and economics. And when I try to describe to people the question that I'm interested in, I usually phrase it as, what inventions are we missing? Which is, of course, an impossible question to answer, but that's, as academics, what we get to have a chance to try to answer. So, as an example, why don't we have a cure for Alzheimer's disease? Lots of people in the economy have answers to that question if you ask them. You can ask doctors, you can ask people that do basic science research, you can ask people that work at private pharmaceutical firms, or people that have been investing in Alzheimer's research at the National Institutes of Health for decades. Many of those people will give you an answer that's roughly of the form, the science is just really hard. And so, economics often gets kind of dinged as being the dismal science, but this is a case where what Hito said before about incentives actually gives a lot more reason to be optimistic. So from an economic perspective, I think we might think that the set of scientific problems that are hard today might be hard because we haven't invested enough in trying to solve them. And so as soon as you kind of allow for the fact that the state of the science today reflects past investments, it immediately opens the box of how can we use policies to try to change incentives and change investments that can make hard problems easier and make progress in areas where it's been stalled. And so that's kind of roughly how I frame my work, is in trying to use data to measure what I think of as missing innovations. So innovations that are scientifically feasible, but that for some reason the incentives just aren't there for them to be brought out to the real world to benefit society. And so given that it's a conference focused on talking about collaboration and why Stanford is a really special place, it seemed like a great time to go through an example where I can use Stanford as an example to talk about collaboration to illustrate one example of how I use data to try to get at these questions. And this is joint work with Josh Lerner, who's at Harvard Business School, and Carolyn Stein, who's currently a postdoc at CBER on her way to Berkeley. This particular project is trying to understand what affects the diffusion of academic discoveries out into the economy. So what makes a difference for whether you're a professor and you publish a paper that maybe some people read and maybe they don't, or whether that paper actually goes out in the world and makes an impact? So people have long tried to argue that universities are a really central source of both commercial innovation and economic growth. But when they've tried to make that argument, they've made it pretty indirectly. And in fact, there's been a lot of focus on why that doesn't happen as often as we would like to in practice. So from a policy perspective, this was a lot of the debate around what's called the Bayh-Dole Act, which basically tried to streamline patent and titling rights to try to encourage university inventions to get commercialized. A lot of the academic research has focused on the fact that in order for the very nascent stage at which academic ideas get disclosed in papers or patents to actually go out and make an impact in the world, it often requires people from the university to go out and work in that translational process. And there's a lot of concerns that maybe there's too few incentives for people to provide their human capital to go out and try to actually co-develop those technologies. And so in this paper, our focus is on a very simple question, which is whether academic discoveries that are otherwise the same but made at different universities have different propensities to spill out into having social benefits for society. There's a lot of variation across universities in whether there's how many patents there are, how many startups there are, et cetera. You could just think, well, some universities are more research active than others, and maybe that's what's going on. But it doesn't take a lot to look at the data and see that that doesn't seem like it really explains things. So if you look at Duke and Stanford, they have very similar research expenditures. They both have a medical school. They are roughly similar in a lot of dimensions of the faculty orientation of their research. Stanford has many more startups than Duke. And so you could say, well, maybe that's obvious. Maybe that's that we're in Silicon Valley. My example is going to suggest that it's not quite that simple. The way that we're going to get at this is looking at how faculty's propensity for their work to impact society changes when they move across universities, to try to get a sense of your research, some component of it stays the same, but whether it's spilling over in different ways to society might change as a function of where you work. And so the example that I wanted to talk about was an example from Stanford, which is Professor Carolyn Bertozzi. So this is one of the many discoveries that's come out of her lab. It's basically a way of doing better, cheaper, faster, more accurate tuberculosis tests. This was discovered in her lab together with a PhD student and a broader range of people. The PhD student was the first author on the paper. Bertozzi and her PhD student and another person from their lab were on the patent. And so Oftentimes, especially in biomedical research, there's a very careful orchestration of disclosing in a patent at the same time you disclose in a paper, because academics want to have a publication but also need to have intellectual property in order to have some incentive for people to come in and commercialize things. And it turns out you need to time those disclosures very carefully, because otherwise your publication invalidates your ability to get a patent. And so that idea of patent paper pairs is something you can measure in data. It's hard to do, but we're working on doing that. But this is a case where, for a case study, it's very easy to come up with ways of finding those patent paper pairs. The idea that it was at the heart of that patent paper pair ended up getting embodied in a startup. The PhD student was named the founder of the company, together with Professor Bertozzi, who's also listed as a founder. The student was placed as the CEO. And again, this kind of illustrates this idea that the human capital of the people that actually do the invention is often seen as necessary in order for the idea to actually get developed. Bertozzi, in this case, was named chair of the Scientific Advisory Board. Many people here are on scientific advisory boards. Sometimes that means more than it does others. From our perspective, it's, if your kind of lab is the one whose work is getting commercialized, you will often be on the Scientific Advisory Board. Many other people will also be on the Scientific Advisory Board, but it's kind of one marker of involvement of faculty in commercialization. So Bertozzi, before she moved to Stanford, was at Berkeley. And so you might think that moving between Berkeley and Stanford doesn't really matter. We're kind of in the same labor market. We're all exposed to the same kind of access to venture capital. We're very close to Silicon Valley. Bertozzi's kind of on record talking about how much her social spillovers of her work changed when she moved to Stanford. And so the way she characterizes her time at Berkeley is the graduate students were excellent, we were doing great science, but I found it hard to think about how to translate my ideas to the clinic. And then she talks about her move to Stanford, where she started 4 companies within 5 years of moving, and she kind of attributes a lot of this to, at Stanford, kind of students from different schools would come to her lab. She would talk with people at the medical school and get suggestions on different ways of thinking about the problems that she was working on, and that the work that she ended up choosing to do was kind of more closely interfacing with kind of the problems that are more in this translational area. So what do I want to illustrate with that example? Mostly it's just meant to say, I think where you work can impact the kind of work you do and whether it diffuses. I don't do qualitative studies, so this is not meant to be a compelling, example making a case for like any particular argument. It's just meant to be an example to motivate why where you work might matter. So we basically try to pull together data to systematically measure academic discoveries and whether they spill over into society, and to measure faculty that move across universities so we can test whether this seems like it matters kind of on a larger scale, not for a case study. So the academic discoveries we focus on are we take all of the data in the Web of Science data, which when I moved to Stanford, Stanford bought a license to the bulk Web of Science data. That's at the library. Everybody can use it. But it's basically all peer-reviewed publications along with some other things. We then track citations to those academic papers that appear in patents. If you are a patent nerd, you'll know that there's a difference between front-page citations, which are sometimes added by lawyers and patent examiners, and in-text citations, which are more often written by the scientists involved in the process. We can look at both of those because we figured out how to extract those both from the patent text directly. And then we can do things like linking academics to the startups that they make and their membership on things like scientific advisory boards to try to measure their direct involvement in the process. Okay. So next, we need to measure where faculty work, which should be easy, except that everybody has 30 affiliations that they list on their papers. So if you go to the Web of Science and you try to figure out where people work, it's pretty hard. Before I came to Stanford, I worked at MIT. I know Sengi Tabatia. She sat next to me at the MIT faculty meetings. I feel comfortable saying she works at MIT, but it would be hard to know that by looking at the affiliations list that you see on her papers. And so what we use as a proxy that's kind of assuming that faculty kind of reveal something when they post an email address on their paper, that you're kind of oftentimes listing the email address for your primary affiliation. So it's not that her primary affiliation is at Brigham and Women's Hospital, which in fact has a completely different technology transfer office and sort of different setup of incentives for faculty. Her main affiliation is at MIT, and her intellectual property goes through MIT. So you can go to this bulk Web of Science data, the XML data, extract the email addresses where they're available, which are mostly for the senior authors, kind of the final authors. That's fine. We're kind of interested in focusing on a sample of people that move, that are research active. And this is a graph which basically just says, it turns out that method works quite well for determining when faculty move. So this is looking at among faculty that move once, by year, relative to the year that you move, what is the share of papers that are in your origin, your home university, relative to your destination? And so you could think email addresses are kind of all over the place, and there's legs in the paper publication process, and this is really messy. It's actually not that messy. So, when I moved from MIT, they canceled my email account. I started using my Stanford account. For a lot of places, that works pretty well. So it doesn't capture everything, but it captures a big sample of movers that we can analyze. Okay. So how many minutes do I have left? This is stuck at 9, so I just... 5? Great, perfect, good. Enough to talk about some results, great. So this is not a graph about the question of interest, but it is a graph that I think is really interesting and informative about what this kind of data can tell you. So this is measuring geographic locations of your citations to your work in patents. So again, the data is constructed by, let's take faculty that move and look at all of their papers that they publish in each year. And the outcome is your paper cited in a patent within 5 years of being published? And in particular, for this outcome, what we're looking at, is it cited by a patent in your origin location, kind of the geographic area where you came from, or your destination location, so where you moved to. So for me, moving from MIT to Stanford, citations from origin is citations to my work from people in Boston versus citations to my work from people in the Bay Area. And so this is nice in illustrating various aspects of the data. So this 5-year citation measure is important because most academic papers, if they get cited in a patent, get cited about 12 years after they're published. So legs are a really important part of the process. We choose this 5-year citation measure as kind of splitting the difference between we need some time for your ideas to diffuse, but if we waited around for 20-year citations, we wouldn't have any data to use. But what you can see with the blue line that's kind of declining, that decline is expected because for papers that were published the year before you move, 4 of the 5 years of your 5-year citations are actually in the place that you moved to. And so I'm gray shading the areas that are kind of contaminated years relative to the move, where those are years that are not cleanly like citations when you're in your origin location. And so what this shows is a variety of things, but one is, so you get more sites in the area where you live. That's not surprising. It doesn't look like there's a lot of concerns about matching. So, it could be my work is getting really heavily used by people in the Bay Area. So before I move there, they're really citing my work, and that's why I move. But in fact, this red line, citations from destination, doesn't tick up until after you move. And so it looks like the process through which knowledge diffusion happens at kind of a local level seems like it changes discretely when you move. The other thing that you can introspect on is that the blue dots after you move are higher than the red dots before you move. And that's kind of saying the people in Boston didn't really forget about me. They're citing me more than if I had never lived there. And so it's kind of giving you a sense that there's kind of a citation bump from moving because just more people know about you and your work, and that's kind of diffusing more in general. Like I said, this is kind of not the main purpose of our analysis, but I think it's useful for giving some mechanics of what happens when people move and how does knowledge diffusion actually happen. This is more along the lines of the actual analysis that we do. So the x-axis here is one parameterization of what's the difference between where you moved to and where you came from. And so when I talk to practitioners about this paper, sometimes they say, oh yes, it's like you're writing about the University of Chicago where good ideas go to die. So there's lots of great universities that are extremely research active that it turns out do not have a high propensity of their work spilling out into patents. And so what this is it's saying, let's parameterize different universities based on the average propensity of papers at that school to be cited in patents. And so if we take, as an example, I moved from Chicago to Stanford, that's a big move in the sense that I'm moving to a place where commercial spillovers on average happen much more. Whereas if I move from Stanford to Chicago, I'm moving to a place that on average commercializes things less. That's essentially what the x-axis is. And so the fact that this is upward sloping is saying, if I move to a place that on average commercializes more, my own work is more likely to spill over into patents as well. And if I move to a place that commercializes less on average, my own work also spills over into patents less. Okay? So that slope is about 30 30%, 0.3, which is telling you that about 30% of the geographic variation in whether academic papers are cited in patents looks like it's explained by where the discovery is made, where you work. Okay. So, of course, there's an 80-page paper, lots of other things going on. I would love to talk to anybody who's interested more about this work. But basically, it's just one way of saying, what inventions are we missing? I think this kind of result, to me, suggests universities have different propensities to kind of have the discoveries at their universities spill over into the economy. And so as we think about kind of what are the latent discoveries that are not realizing their social impact, these kinds of estimates about place-based factors I think can be really important as an input into that. So most of my previous work had been focused on what happens when the patent system is poorly designed and what happens when the NIH grants are kind of designed poorly. And all of those I think are also important, but I think this idea that where you work might really matter for whether your ideas have a social impact is important in a lot of dimensions. So thank you for the opportunity to present.
Thank you, Heidi. So our next speaker is Phil Marshall, who is a senior scientist at SLAC, a National Accelerator Laboratory, and he's going to tell us about scaling up astronomy at the Vera Rubin Observatory. Welcome, Phil.
All right, thanks very much. Nice to see you all. It's my first live talk in 2 years, so I'm actually feeling a bit nervous, so bear with me. Okay, so I'm Phil Marsh. I'm from the Kavli Institute for Particle Astrophysics and Cosmology. Some of you know it, some of you don't. It very helpfully connects the physicists and astronomers at the physics department on campus with high-energy physicists like me up at SLAC. And it's been really great for more than a decade now at doing that. Here are some of the names of the people I work with at KaiPak on a particular measurement we're trying to make in cosmology. I'd say we may not have the best questions, but we certainly have questions that are both fundamental and fun. And so I wanted to show you a little bit about what we're doing with in data science at KaiPak. So let me see. Okay, so fundamental and fun problems. You may not have caught this from the news over the last few years, but the universe's expansion is accelerating. Nobody knows why. It's a bit odd. What goes up must come down, except when it comes to the whole universe. So one of the things we're trying to understand is dark energy. What is it that's accelerating the expansion? Another thing we're trying to figure out is what is our galaxy made of? Turns out 90% of the mass of the galaxy is in dark matter, and we have no idea what it is. So we're trying to take astronomical data and ask these hard questions, or rather make the measurements that will inform the theorists who are coming up with the ideas for what might be going on out there in the universe. So we are about making accurate measurements from large amounts of astronomical data. And at the moment up at SLAC, we're very much focused on Rubin Observatory as a source of data for us in the next decade. We've been busy building the world's biggest digital camera. There it is. 3.2 gigapixels. It's in the lab up at SLAC. It'll be shipped next year to an observatory on a mountaintop in Chile. That's the Rubin Observatory. What will we do with Rubin? Well, it's a wide-field camera attached to a telescope with a very big mirror that can collect a lot of light. Makes it very fast at surveying the night sky. So for 10 years, 2024 to 2034, we'll repeatedly image the entire southern sky and build up an 800-frame movie of the sky in 6 optical and near-infrared filters. All that imaging, hundreds of petabytes of pixel data, every night and then once per year for annual releases, we'll run automated measurement pipelines on those images to make trillions of measurements of billions of objects, stars, galaxies, supernovae, everything. We'll see things change with time. There'll be time series for everything. It's a huge database for everybody to mine. So people like me and the others at KaiPak, we're building data scopes to observe this database, essentially. Okay, to give you a flavor of the kind of data we'll get from Rubin, here's a small patch of sky. That brown stripe is supposed to represent a hair held at arm's length. Look at all those galaxies behind a hair. There's a zoom in there. You can see next to the hair there's a funny-looking object, some blue arcs arranged around some orange blobs. The orange blobs are massive galaxies. The blue arcs are distorted images of a background galaxy that's being gravitationally lensed. These are rare objects, but they turn out to be very useful for studying dark matter and dark energy. Okay, so here's a picture of gravitational lensing in action. On the right, there's an image of what you see in the sky, 4 images of the same background bright point source, an active galactic nucleus in this case. Those are interesting to us because they flicker, and the flickerings arrive at the telescope at slightly different times, maybe offset by a week or two. We can use those time delays to measure the distance to the massive galaxy that's doing the lensing. And that distance is what allows us to make accurate measurements of the expansion rate of the universe. So we're interested in measuring time series, measuring time delays, using them to measure distance. We can only do the distance measurement if we model the mass of the galaxy extremely accurately. Not just weigh it, one number, but map out where the mass is, how much dark matter there is, how much stellar mass there is, and do that very accurately. Another thing we can do with gravitational lenses, we can look at those blue arcs and look at tiny little perturbations in their brightness across, around the arc, across the arc. Those little perturbations we think are caused by clumps of dark matter. No one's ever seen any dark matter, but we see it gravitating, and we think it forms small clumps, smaller than galaxies, that make little differences to the arcs. And so one of the things we want to do is build up samples of lenses that we can use to probe this clumpy aspect of dark matter, and through that get a handle of what it might be. All right, so Reuben will give us large samples of lenses, maybe 10 to 100 times more than we have right now. And so that's our own big data problem. In fact, many astronomers will have the same big data problem coming from Reuben. The samples of objects that they're interested in will suddenly get very much bigger, and they'll have to change the way they do their data analysis. So that's their own big data problem. Why do I say their own big data problem? I think all big data problems are personal. If you've had to change your analysis approach because of the velocity or the variety or the volume of your data, you have a big data problem. Here we are in group therapy for our big data problems. Okay, so we're trying to analyze much bigger samples of lenses, but not compromise on the accuracy of the modeling. So can we use deep learning to do this? We think yes. So here's what we've been doing the last couple of years. We build training sets of synthetic gravitational lenses and train various deep learning networks to do the inference that would have taken a few days before, grinding through the forward modeling with MCMC. We now try and make neural posterior estimates in under a second, and then spend more time trying to make accurate predictions with those so we don't get the huge speed up. But we're asking, can we get orders of magnitude in speed up, computation time, in order to approach these large samples? When we make the training set, we have to make some choices. We have to make a model of the galaxy population in the background and also the deflector population. And we'd like to not to have had to have made those choices, but since we did have to make them, we're going to have to live with them. And so a lot of what we do is try and tackle the problem of unrepresentative training sets, try and hierarchically infer the populations of galaxies at the same time as the cosmological parameters we're interested in. So here's a PGM sort of high-level probabilistic graphical model for what we're trying to do. We have cosmological parameters on the left. One of them is called H0. That's the current expansion rate of the universe. But we also have hyperparameters that describe these populations of galaxies. And then we're trying to work with image data, so high-resolution images of these gravitational lens systems, also measured time delays coming from the time series. Here's an example of one of the tests we've done. This is Ji-Won Park and Simon Vera. Simon's here in the audience somewhere. They made a little test set of 200 mock LSST lenses, as might be discovered by Rubin Observatory. We imagine that each of them has a measured time delay and some high-resolution imaging. And the question is, can we model them with Bayesian neural networks without introducing bias in H0? And in this test, the answer seems to be yes, that was good. Why do we phrase the question like that? Turns out there's some skepticism in astronomy about machine learning, and can it really be used to do principled scientific inference? And that turns out to be the same question we have. We want to do things right as well. And so a lot of what we've been doing lately is using these new methods and just checking that they really can give us the accuracy we want as well as the speed up we need. We've been using graph neural networks to try and understand the catalogs of galaxies in the vicinity of these strong lenses. It turns out all of those galaxies along the line of sight can perturb the gravitational lensing effect a little bit, and we have to take that into account. So we have to model the environments of lenses, and the question is, can we use graph neural networks to use more information from the catalog than just counting up the number of galaxies to see whether it's an overdense field or an underdense field? This seems promising as well, that we get some increase in precision from using those that extra information. And so far, we haven't introduced bias by doing the inference fast with deep learning. Here's Sebastian Wagner-Carrena, one of the SDS grad fellows. He's been working on the dark matter problem, and he sees it as a sort of extreme hierarchical inference problem. Imagine a gravitational lens system where just in this little postage stamp image, there may be 1,000 clumps of dark matter in the lens, and another 1,000 along the line of sight of the lens, and you can't see any of them. But they cause little perturbations to the rings, and we want to understand the statistical properties of that population of dark matter clumps. And so he's been trying to use, again, samples of 10, 50, 100 lenses, see whether we can back out the population of parameters or hyperparameters that describe the population of clumps without introducing bias. And so far, so good. There's a small amount of signal coming from each lens. The combination of 100 or so give you fairly tight constraints on the population. That's the bottom figure is some illustration of the population. Again, we're getting there without introducing bias, and so he'll keep investigating this. Encourage you to look at his poster later on today. Okay, so that was a whistle-stop tour just through the strong lensing work at KIPAC. Just some comments on what we're trying to do with Reuben. These inference problems in astronomy are generically hierarchical. Why is that? Well, we only get to see each galaxy at a single point in time from a particular orientation, so we have no choice but to try and understand fundamental astrophysics by building up large samples of galaxies that we see from different orientations at different points in their evolution. Then we're interested typically in a small number of hyperparameters that describe populations, whereas we have huge numbers of nuisance parameters that describe individual objects, which look pretty but aren't actually of intrinsic interest on their own. Strong gravitational lenses are interesting not just if you're trying to tackle the particular questions I'm interested in, but because they're hard to model. They have this non-linear lensing effect, so their careful modeling is needed. So our hope is that by solving the hard lensing problem, it will make it more straightforward to tackle easier problems around astronomy. And I guess our conclusion so far, after a couple of years of exploring deep learning, is that neural posterior estimation seems to be a very promising route to getting orders of magnitude speed up without introducing bias. Okay, so there are many others at KIPAC doing data science, trying to do science with data. Our data are typically sparse, blurry, low signal to noise, contaminated with artifacts and other systematic effects. I was pleased to see lots of these listed by other speakers this morning, so I'm not on my own here. But it is true that some of the techniques developed for higher fidelity data, so for example, natural images, look promising, but they may not be applicable. So some of our research is testing those methods in this different regime. You probably have had some of the same experience. If you do see some reflection of our work in yours, then it'd be great to swap notes. I now have some business cards for you from 3 other people at KIPAC, just to show you what else is going on. Here's Tawiwa Sombon-Ponyako. He's here. He works in the sort of extreme low signal to noise regime, Xray Astronomy, where every photon counts, trying to model galaxy clusters by their X-ray emission, and again in larger and larger samples. Here's Dominic Beck. He works on a particular inference where the likelihood depends on having done lots of expensive numerical simulations of the universe. He doesn't want to make very many of those simulations, but somehow has to cope with the fact that he doesn't have that many of them. And then here's Maria Elena Monzani, who works on the LZ experiment. This is an underground dark matter detection experiment, so another way of trying to understand dark matter. And they're trying to use machine learning for anomaly detection and uncertainty quantification. As she puts it, the extreme needle in a haystack problem. So that went past fast. There's a lot of words on those slides that I didn't say. They're sort of designed for your future selves. If you find yourself interested in, oh, what did that chap from KaiPAC say? You can go back and look at these slides and read in a bit more detail. But I wanted to end with this picture. This is a representation of the strong lensing community at KaiPAC. And I tried to draw people according to their shape, at least as I see them. So we have a couple of T-shaped faculty with their broad knowledge, providing some basic scaffolding. Then we have three gamma-shaped fellows. That is, we have long legs in our domain of strong lensing, but we've put some effort in over the years to understanding statistics, machine learning, and so on. But those legs don't really reach to the ground, so we have to lean on each other. And then at the top, what we've ended up doing is supporting graduate students who really are pie-shaped. So Sebastian and G1, and we hope Sydney, who did a rotation with us, are learning the machine learning, learning the strong lensing, and coming out skilled in both. G1 just got hired to Genentech, so a success story for other grad students in the crowd. Last thing to note, though, the one thing that we're really missing from this is someone with a long leg in statistics or machine learning. And so I put in this little crutch here called STS. That's what I'm hoping to get out of hanging out with all of you. Thanks very much.
I think, Phil, on the question of what is dark matter, just put in a solid bid for the best research question. It's my pleasure to introduce our next speaker. This is Mark Hansen. Mark is the David and Helen Gurley Brown Professor of Journalism and Innovation, and also the director of the David and Helen Gurley Brown Institute of Media Innovation, Columbia University. And his title is How Things Really Are. Thank you.
Thank you. So I'm assuming the big green button is what I want, right? Yes. And I go back. There we go. All right. Thank you. Good afternoon, and thank you for inviting me to be part of this celebration of data science and the opportunities it holds across this and every campus. My talk today is about a quote within a quote from John Tukey, How Things Really Are. I chose it not because I know, but because the drive to find out is what motivates a careful data analyst. She's curious, she thinks beyond a single data set, she asks questions, she interviews people, she's an investigator. And for the purpose of this talk, I'd say in Tukey's vision, she's a reporter. 10 years ago, I joined the faculty at Columbia Journalism School. Prior to that, I had the good fortune of working with some amazingly talented artists, creating installations that represented often complex data to the public. Here is one in the lobby of the New York Times, a grid of screens using machine learning techniques to create a portrait of the news of the day, word by word, sentence by sentence, article by article. This is my favorite image of the piece. It's a shameless photo bomber. Our artworks involve large and live data sets that we distilled through combinations, or that we distilled through sometimes playful, sometimes technical displays. I think that was what got me the job at Columbia. I had a background in statistics and had a sense of the narrative potential in data. It didn't take long for me to realize that this connection between data and narrative was hardly new for journalism. Even Joseph Pulitzer himself, founder of our school at Columbia, wrote in the North American Review in 1904 about his College of Journalism, my college, and what should be taught to promote the welfare of the Republic. In his essay, in addition to law and ethics and history, courses we offer today, he includes statistics or data. Everybody says that statistics should be taught, Pulitzer wrote, but how? You want statistics to tell you the truth? You can find truth there if you know how to get at it, and romance, human interest, humor, and fascinating revelations as well. Think of that. Romance, human interest, and humor. Pulitzer saw tremendous narrative power in data. All that said, as soon as I stepped into my first class, I realized that my training as a statistician didn't prepare me to deliver on Pulitzer's promise. One of the first student projects needed a feed of crime data from the NYPD. I was stunned to find out that while each week the department reported precinct-level incident counts, it did so by overriding the previous week's data. The department was in a perpetual now, and anyone who wanted to look back over recent history needed to be scraping it. Why? How could that be? One of the big lessons for me over the last decade has been how much we should know but don't, and how gap-filling is a first-order action in data journalism. For example, from the HHS, we have only sloppy voluntary counts of the number of healthcare workers at each facility who are vaccinated against COVID. We still don't have an accurate count of the number of people who are killed by police each year, but here news outlets like The Guardian and The Washington Post have stepped in using largely targeted Google searches to come up with better numbers than the FBI publishes. During the height of the COVID pandemic, the Atlantic's COVID tracking project provided data on testing that was not easily available elsewhere, and my own institute's documenting COVID-19 project used targeted FOIA requests to city, county, and state officials to understand how decisions were being made about the pandemic. Over 100 articles have appeared from this group, and recently they published data on coroner practices and undercounting of COVID deaths. In retrospect, I should have seen all of this coming, but from the perspective of the statistics classes that I took and the classes that I taught, data absence wasn't really discussed. The next hurdle for me was the basic act of reporting. This took me some time to fully appreciate. To describe what I mean, I'm going to refer to an article in the Columbia Journalism Review by Philip Isle. He's a freelancer from Rhode Island. The piece is called Ode to a Reporter's Notebooks, sorry. We've all seen portrayals of journalists on television shows and movies, notebooks in hand, scribbling furiously. For Isle, however, a reporter's notebook is more than paper and cardboard. It symbolizes the power and uniqueness of journalism as a profession. In his words, this object is a license to talk to interesting people and a ticket to interesting places. The key to bringing these people and places to life, he writes, is to capture and convey the details. And the reporter's notebook is how Isle captures the sights, smells, sounds, feelings, tastes, and other impressions of the world. To report, he writes, is to be alert and alive in a particular time and place. That's sort of worth repeating. To report is to be alert and alive in a particular time and place. When I arrived at the journalism school, I was told over and over that journalism is less an academic discipline than a habit of mind. We cultivate in our students a curiosity about the world, a restless questioning spirit that asks why things look as they do. And my role as a statistician in a journalism school is to add computational lines of inquiry to this habit of mind. If you take one thing from my talk this afternoon, it's that just as the reporter's notebook represents a call to be alert and alive in a particular time and place, understanding the computing systems we rely on daily opens our eyes to new aspects of the world, to see and interrogate the data and algorithms that increasingly govern how our society functions. And all this brings us, hopefully, to Tukey and the careful data analyst who knows how to be alert and alive and how to get at how things really are. All right, time for an example. Each spring, I teach a course in computational journalism. I'm going to present one of the data stories coming from my class. It's a couple years old, but it's a good example. Our reporter's notebooks have been replaced with the Jupyter and Colab notebooks, primarily in Python. Here's one of the notebooks. Here's the notebook. It's on bots. The bots are a great example because students can use bots both to report with as well as on. I'm going to take bots as a kind of case study for the rest of this talk because they have been particularly influential in spreading information and misinformation about voting and elections and vaccines and the war in Ukraine. As you all know, bots serve different purposes. There are bots that notify and bots that inform. Here's one that alerts you when a new word appears for the first time on the front page of the New York Times. And then there were pandemic-inspired bots. Recently, Twitter has tried to make bots like these a respectable part of their ecosystem. This is one that tweets out the location of jets owned by Russian oligarchs. It carries a new designation from Twitter, complete with a robot badge and mention of the author's Twitter account. The idea is to promote trust in these good bots. But then what about the bad bots, the bots that amplify? So what do I mean by that? Well, this is John Leguizamano. He's one of here is one of his tweets. "I'm good. You?" he writes. Somehow this statement earned him 34 likes and 4 retweets. Who are the people who find this worthwhile to amplify? So here's Kim Hill. You have to wonder how she had time to pose for this image, given that she has 86,000 tweets in 2 years. That's about 10 tweets an hour for a 12-hour day every day of the year. And then Marquise Martinez, his account looks fairly respectable until you read that he's from Emeritus, a city in Georgia, and claims to be the dean of the Harvard Medical School. In my class, one of the issues we tackled was how we could be sure an account was in fact a bot. It's a dark art and offered an opportunity to teach the students about machine learning. There are services that can help, but they're noisy. Clearly, though, Marquise is a bot. Given all this, my class wondered what kind of influence we could have. So we opened up a Twitter account, and we did a Google search. How do we get more followers on Twitter? We turned up an answer. We could just simply buy them. So we found a company, Devumi, that seemed highly rated, which only later we realized was because the company's CEO was an SEO expert. It promised amazing growth, and the process was simple. Essentially, you pay them, and followers would come flocking. And so we did, and they did, and we bought 2,500 in total. I expected accounts like Kim Hill and Marquise Martinez. Instead, we had accounts like these. They look great. Biopics match background images. Facebook and Instagram links pointed to accounts featuring the same people. These were real, but the economics didn't work out. We paid a couple of pennies for each follower. So why would anyone follow us just for so little money? It didn't make any sense. But then we noticed a tell. Every bot, a clever bot maker had simply lifted people's data and created new accounts with a slightly altered name. Lowercase L's became I's and vice versa. O's became zeros. And underscores became doubled. The strategy works well because our actual login name appears only in small gray. Thank you. Works well because it appears in. Sorry, I've got to come back. I know, I don't know, because the actual login appears in small grade letters on the Twitter interface. The bot maker was indiscriminate, young, old, couples, adults and minors, all transformed into bots that went on to tweet statuses from Devumi's various clients in multiple languages, often political, often heavily pornographic. From our 2,500 purchased followers, we spidered the network and came up with 50,000 stolen identities, some stolen many times. After all this, we decided we had a story and we brought it to the Times. A year of computation later, this appeared. Buying influence from a shadowy market, and online it looks like this. So here's some examples, or an example, given that it's 3 minutes and 8 seconds. This is Chef Simon, an Iron Chef and then co-host of ABC's The Chew. He bought hundreds of thousands of followers from Devumi. In the plot, each blue dot is a follower. On the x-axis is the order they followed the chef, and the y-axis is the year they joined Twitter. For the first year or so, everything looks okay. This is what organic growth looks like, a slow hill, because as time goes on, people join Twitter and then follow the chef. But if you look at all of his followers, what you'll see is the stripes. The stripes indicate groups of accounts that follow the chef all at about the same time and join Twitter all at about the same time. This is a clear indication of bot accounts, as bot makers will often make their accounts in bulk after perhaps acquiring a list of stolen email addresses. The story behind the company itself is fascinating. It turns out they don't really make any of these bots themselves. Instead, it's a kind of arbitrage scheme with Devumi buying followers from a third party, places like Peeker. The fallout from our article was pretty intense. Hacker News said, basically, if a bunch of journalists could do this, why can't Twitter engineers? Which I took as slightly insulting, as the whole purpose of this class was to prepare journalists to do this. But anyway, a couple of people were embarrassed and threw their aides under the bus. Attorneys general at different states opened cases. The Senate directed the FCC to look at impersonation, and lots of bots on Twitter, millions of bots died on Twitter almost overnight. And then California, you're welcome, got a bot law, again referencing our piece. There is so much more to talk about in this example. How does a news outlet trust the work that you've done? How do you explain data science to your editor? What habits do you adopt to make these questions easy? I'm going to get this finished even before time, Chiara. But I'll leave all that discussion about trust to the next panel. That said, I hope with this example you see how Tukey's quote feels like a call to report. There's a dynamism in Tukey's description of exploratory analysis as investigation. It is similar to the call to be alert and alive. So far, I've emphasized what it means for the practice of journalism, how the introduction of technical tools helps journalists both report on as well as with computation. But there are lessons for data science as well. The call to be alert and alive in a particular time and place is the backbone of a potential public mission for data science. Look up, get involved, ask questions, talk to people. Philip Isle finishes his ode commenting that the reporter's notebook is one of the world's greatest mechanisms for accountability. Again, from the data science perspective, the reporter's mindset can be an entry point for an aspiring data scientist, an invitation to question the often invisible but undeniably powerful computing technologies that shape our daily lives. Thank you.
So I'm going to ask our speakers to join us up here at the front and take a chair, take a seat at the big long table. Okay, we have a question up here. I don't know where our microphone, and one back there. Go ahead.
Just thought I'd get started with Dr. Williams. So in looking at the sort of the positive assorted mating of scholars in Stanford, how did you account for the fact that the kinds of scholars who want to move here might be exactly the ones who are more interested in certain kinds of translation and team science? And I've seen that in my own discipline and many other disciplines, that there are people who are perfectly happy with the winters or whatever in their home institutions, and there are those who actually want to get patents and start businesses, and they have a different DNA even before they move.
Yeah, great question. These kinds of questions are places where I feel like theory and data are really complements in kind of trying to think about what are the different mechanisms by which this might matter. And so one thing is when you move to a new place, some of your work comes with you, right? Your past work. So how does citations to the work you did before you moved change versus, what's different about your work? Are you working in different directions? How do things change after you move? So when you're working with data like full text publication data, full text patent data, it's just a very rich setting to be able to talk a lot about, what happened to my work at my old institution? Was that converging to be more like the research that's done at my new institution before I moved? How is the work changing when I actually moved? And so those are all things that, we're still doing a lot of the text analysis to be able to do that. But I think just conceptually, I think there's like a lot of interesting experiments in the data that let you get at different mechanisms that I think shed light on different behavioral margins that might matter. So.
It's a question for Phil about sort of where the data scientists sit in physics. So you have this this real distinction between like the theorists and the experimentalists, right? And so I'm curious, like, have the data scientists emerged from one side or the other? And in part this is flavored by thinking about data science as an interdisciplinary sort of enterprise and the challenges that people who sit at that sort of nexus often have. So I'm curious where they're sitting, and have they been sort of, have people who do data science and physics been able to go on and get jobs in physics and be sort of, embraced by one side or the other?
Yeah, it's an interesting question. I'd say mostly it's more on the experimental side. People trying to make measurements have got interested in more and more sophisticated ways to do that, and ended up being drawn towards the data science communities that are forming. But it's not entirely true. We had one pair of postdocs who actually pioneered the machine learning work that we then picked up on. One of them came from the theory group, and the other came from the observational side of CAIPAC. And they worked worked it all out together and then have carried on in that way. So I think it's piqued the interest of people across astronomy. And it might be just because of, the nature of our field. It's hard to make measurements in astronomy. And the theorists see that as well as the experimentalists. The experimentalists feel it, but the theorists see it as well. And so it has some draw for everyone. In terms of where are people getting jobs, I think the postdocs who are applying for faculty are seeing a few more opportunities in more data science-oriented ways, joint positions, that kind of thing. But it's I wouldn't say it was really taking off around the country. I think what they'll do is they'll take their short legs to their new departments and just continue the process of seeding data science initiatives there. And then it's nice to be able to, it's nice to see the grad students and postdocs who really get into data science becoming really quite attractive to industry, especially around here. And that's been really good to see.
Hi, this is a question for Mark and for Brad. I've seen some really bad examples of computational journalism where some company will exploit cherry picking to make their product look really good and kind of pull the wool over the consumer's eyes. My question is, what can reputable statisticians and journalists do to help these consumers out and mitigate this problem?
Would you please repeat?
Yes, the question is, what can we do? Tell me if I get this right. What can we do to help people better understand the data that's being presented to them and from reports and studies that are coming out?
It's a question of how we can interpret things better, or?
No, I've seen some really bad examples of data journalism where they basically exploit selection. They really pick out things, and the consumer gets really excited because it looks like there's statistics and there's data science when there really isn't. Yeah. And my question is, what can reputable statisticians and journalists do to combat that?
Yeah. So that I don't have a specific answer, but I do. It does bring up the question of covariance. The analysis I gave sort of lumped everything in the world together, which is what the Cochrane database does. But there's covariance. Like if you knew that this journal is a terrible journal and they just go out of their way to exaggerate, you'd feel differently. I feel differently when I read something in the New York Times than if I read it in the Daily Post or something like that. So the answer is I don't know how to do that. In some sense, it falls more into your brain.
Right. Yeah, so I think when I first started at the J School, there was one data-related class. It served 16 students a year, and that was it. As a course, for a semester. And now about half of the cohort takes some kind of data training. So I think there's one thing is to simply up the overall literacy of even sort of the rank and file journalists who aren't going to go into sort of big heavy data work. There's also, I think, newsroom practices that help protect against sort of mistakes. Now, if an outlet's going to intentionally deceive, that's a different question. But to keep them from making sort of rookie mistakes is something that training can help with, and editorial process can help with, I think, too.
So I keep scorecards on data, that the various journals and things I might read. So, for example, does you get a brochure from some place, maybe their newsletter. Does the newsletter ever have anything against their main point of view? That's a real good sign. Have they ever changed their mind on anything? That's another good sign. So, yeah, you can watch.
That idea of a report card. I think we can take one more question, David, and it looks like that's you.
This is a pretty simple question, but I guess it follows on is, if I understood, Brad, your talk, it wasn't totally symmetric, the Cochrane database. It seemed like the the positive effects got shrunk differently than the negative effects. Did I see that right? And what's different about studies that are finding positive effects from studies that are looking at negative effects.
No, could you say?
So there was some asymmetry in the effects, the positive versus the negative, and he was just asking what.
Why?
Yeah.
Why is it not symmetric?
Why is it not symmetric?
That's a very good question. It worried me about the Cochrane database as to why it's so symmetric. It worried Eric Van Zweet also. You'd sort of think that it would be more positive, maybe if the Z values were always the treatment minus the control. You'd think that most of them would be positive, right? I tried to find out something about the Cochrane database and sort of failed. It's a really interesting, the amount of stuff I showed you is a very small amount of the things they have. And I did not succeed in really understanding why there was that symmetry.
So let's thank our speakers one more time.